Hello, Keith Rucker here at VintageMachinery.org. Guys, today we are back to working on the antique metal planer that we are in the process of restoring. And in a previous episode, I had come in here and done some leveling to this machine to kind of get it ready to do some more further alignment testing and make some fine tunes. And over the last day or two, I've been slowly tweaking this machine in and getting it further aligned up. I wanted to share with you guys a little bit about the process that we're doing it. So if you're not familiar, this machine, we had it sent off. We had the ways reground in it. We brought it back in, put it back up on its original legs. There's 3 sets of legs, one in the front, one in the very back, and a set of legs in the middle. When I did my initial leveling, I used a Fell precision level, extremely accurate level. I worked on basically just adjusting the ends to get the bed level, and I could tell that there was a little bit of a sag in the middle just by taking the levels out to the end. So I came back in, and this was kind of off camera. We started adjusting the feet over the middle until I really kind of got everything reading more or less the same on my level on the ends as well as directly over the legs. Now from there, what I wanted to do was I wanted to actually check the alignment of these ground ways. These were fresh off the grinder. In theory, they should be pretty near close to perfect, but I know from past experience, just working with machines, this bed's 10 feet long, and when you take it off of a very stable grinder where it was sitting pretty much on its entire base and put it on 6 points of contact or 6 different feet, you can get twist, you can get movement in that metal. And you can actually very easily, by adjusting those leveling points, you can move this thing a lot more than people really realize. And case in point, I'm going to kind of cut to the chase here. When I first measured the alignment of the ways, here in the middle, we were sagging about 6/1000ths of an inch, which is a fairly significant number. After doing some jacking in the middle and adjusting those feet in the center, I've really got this thing down very, very close to being perfectly flat. It's within less than 1/1000th of any error from one end to the other. That's over 10 feet, which is well within spec for this machine. It's actually about half of what the maximum error that's allowed. So we did a very good job of getting everything worked out. What I specifically want to talk to you today, though, about is using this tool right here that I've got set up. This is an autocollimator, and I use that to actually check the flatness of these ways. Extremely accurate precision tool used for doing just like this. This is one of the things you can use it for, is way alignment. And I'm going to talk a little bit about the autocollimator, how it works, so there's no black magic going on here, and then show you how we did this on this machine and show you the results after doing some tweaking. So first off, let me show you the actual autocollimator. So this is the instrument. It's sometimes called an alignment telescope. Its technical term is an autocollimator, and we'll explain why it's called that here in just a minute. But basically what you've got is you've got a kind of a telescope looking piece here. There's an eyepiece on this end. There's a place for a light source. There's a flashlight. You stick it in on the side here, and that goes into a mirror which reflects a light beam out the end of the telescope. It goes to a mirror. This is a precision mirror. This mirror is extremely flat. It has to be for what we're doing. It takes that light column that we're shooting toward it, it reflects it back in. There's a set of crosshairs in here that we're actually projecting through that mirror, and as we move this mirror here, down the machine, what this instrument does is it detects any changes in the angle. In this case, we're looking at the angle in this direction. And from that, using some math, I can calculate changes in actual elevation. This autocollimator is extremely accurate. I can basically measure an angle down to about 1/10 of a second. And to give you an idea of that, so remember that a circle has 360 degrees. Each degree is divided into 60 seconds. 60 minutes. Each degree is divided into 60 minutes. and each minute is then divided into 60 seconds. This instrument can detect a change in angle in 1/10 of a second, which is extremely, extremely accurate. So I'm going to go over to the whiteboard and kind of show you how this thing works, and then we're going to show you how we use it. So I've kind of got an illustration here kind of showing the basics of what's going on. So first off, you need to understand that when you have a light source, if you take a flashlight and you turn it on, the light is going to radiate out. So if you were to come in here and had a wall here, this would be X number of, feet apart. If you went out twice that far or whatever, it would be your circle that you would draw from that light beam would get larger and larger and larger because those light beams are radiating out at an angle. With an autocollimator, what we're doing here is we have a light source that comes in. It hits a mirror, reflects that, changes the angle of that light 90 degrees. It goes out to a lens in the end, and this lens is a collimating lens or collimating lens. And by collimating, what it does is it takes this light beam that goes like this. When it hits that lens, it makes the light beams parallel to one another, or columns. That's where collimator comes from, is as columns. So these light beams now are exactly parallel to one another. So if you were to again draw, come in here and measure the diameter on the wall at 1 foot away from it versus 10 feet away from it, that diameter of that light beam would be exactly the same. So we're collimating the light. It goes out and it hits the mirror. And I'm showing here the mirror has a tilt to it. And that mirror purposely has a 1 second tilt to it. And depending on how you got things set up, it may be a little bit more or less than that. But that light is going to reflect straight back to the autocollimator. It goes back through that same lens and basically converts it back down to a single point. There's another lens here that goes into your eyepiece and lets you see what's going on. Now, the secret to how this thing works is that there is a set of crosshairs inside the autocollimator. And when the light goes through that crosshair, it's actually projecting that target, that bullseye, over to the mirror. And when it reflects back, you actually see in there another set of crosshairs, which is the reflection that's coming back to you. And what we do with this is as we move that mirror down away from the instrument, this line here, we're really not worried about this one here because we're only measuring in one direction, but this line is going to move up and down. And there is a little micrometer tool built into the autocollimator, into the site where you can look into, and you can adjust that. There's basically 2 lines. I got it kind of showed here on the red. It's just 2 little lines. I'll try to get a picture of looking through the eyepiece. I tried to take a picture with my camera, and I just can't get it to work, but I think I can find what it looks like through there. But what you do is you can adjust these 2 parallel lines up and down till you get them exactly right there in the middle of this line that's projected. And then you can just read directly off of there how many seconds of an angle change it moved by seeing how that line moves. So as this thing moves down here, this line is going up and down depending on the angle. And then again, using math, we can turn that angle measurement into a height measurement. So a little bit complicated, but hopefully that kind of takes the mystery out of what's going on here. When we're using it, we're basically just adjusting that micrometer feed up and down to match that line. We read the number off of the micrometer that's on there, off that scale, and that gives us our angle. And we're looking at relative angles as it moves down through there. Not really absolute angles. We're just looking at what's our start, what's the angle next to it, compare those to one another. And again, the math, we can figure out the height difference. So that's how an autocollimator works. Let's show how it works in practice here. So I have a copy here of the instructions that came with this Hilger Watts autocollimator. This is actually a reproduction, and Tom Lipton over at Ox Tools actually had an original. He scanned it in and sent it to me. It's actually up on the VintageMachinery.org website if anybody's interested, under the Hilger Watts section. But in this, it gives you instructions on how to measure the change in error or whatever across on ways. There's a whole section here on that. It talks about how to set up to do it. It talks about how far apart your pads need to be for whatever you're doing. And there's an example that shows the math involved to do it. So I kind of cheated. I took all that information and I actually put it in an Excel spreadsheet where I just put my numbers in here and it just calculates everything for me. And I used the example in the book to set that up. That took me a little while to get done, but boy, what a difference it makes. So first off, when you're looking at this, you want to have the distance of the feet on your mirror be appropriate for the length that you are measuring. In an ideal world, you want that length here to be 1/12 of the distance of whatever you're measuring. And so we did the math, and on a 10-foot bed, it's actually, I measured in inches, 127 inches, not exactly 10 foot, but the ideal mirror length, our base of the mirror would be 10.583 inches. So when I made my mirror sled, this is actually 10 1/4 inches from one end to the other. So that tells me, think of this as a triangle. If you've been looking at math, the whole right triangle and the Pythagorean theorem, you can figure out by your angles, you can figure out the difference in the heights from one to the other. So as this mirror's going along, it's moving up and down, and I'm exaggerating those changes, but by very small amounts, it's moving up and down. And for this particular setup, with that mirror length, for every second of an angle that it moves, it's about 51 millionths of an inch in height. So very precise measurements here. And what we're doing, again, we're reading those seconds off as we go. So what I do is we shoot this here. We just look through the eyepiece. I start at 0. I look in there. I read what my angle is. What that angle is, it really doesn't matter, because it's relative as we go across. I'm not trying to make that 0 or anything like that. We just, whatever it is what it is, and then we write that number down. In this case, I put it into the spreadsheet. I then move the mirror down the length of the base, which is, again, about 10 1/4 inches. I look through there, I get another measurement. I move it down, I look through there, I get another measurement. This is mapping out those changes in the angle as it goes across. I'm putting it in the spreadsheet, and when I get through the last measurement down there, it will then take those numbers and it will actually mathematically calculate. Basically, what it does is it forces both ends to 0 and it calculates the deviation in height across this entire length. And I'll show you my results. I did both sides here. Did them separately from one another, and let me show you the results of what we got. Again, if you want more information on how all this math is done, look in the manual that I showed you a while ago. It goes through how to do this, but basically all I'm doing is I'm reading the seconds off of the autocollimator, off of that dial, and we have it to 1/10 of a second. And for each position on there, which is 10 1/4 inches apart, I write down the number that I get. And it starts doing a bunch of mathematical stuff here. And at the end, when you get through, really, it's as you go, it's also drawing a graph of what's going on. This is greatly exaggerated. It's not really a spaghetti noodle like that, but in fact, the last line here is only 1.5 thousandths of an inch over 10 feet. So, very small numbers here. But at the end, it tells you your error. So when I did the left side of the ways, again, this is what I got. And again, that's extremely exaggerated on the graph, but it really kind of shows you what's going on. It kind of dips down. This is the end. This is roughly where my leg is, and this is where a leg is. So you see a little bit of a sag between each legs. This leg's a little bit closer to the front end than the leg on this side. So the sag is a little bit less on one side or the other. All in all, the worst error in there was about 1.3 thousandths of an inch over 10 feet. When I look up the specs for this machine, to be within spec for a bed this long as I'm under about 2.5 thousandths of an inch maximum error, I'm actually within spec. So we're well within spec on this one. And then when I check the right side, Let me switch here. I printed this one out too. Shows a similar type pattern. We kind of go down, it comes back up, and got another little dip at the end. On this one, it was only a little over 1/1000th of an inch of total error in the worst spot. Again, well within spec. There was only about 3/10,000ths of an inch difference between the two sides. And guys, if I start trying to adjust things, I'm really just chasing my tail. We are well within spec on this machine, and I just decided, okay, when I got to this, we're calling it. That's what it's going to be. But again, this is very exaggerated, but you kind of get an idea of what's going on along the length of that way. There you go. That's a little bit of an overview of us using the autocollimator to measure the flatness of the ways on this machine. And that was just one of the tests that I did when I was checking things out here, was just looking at the actual up and down as it moves down through there. And hopefully this makes some sense to you. I know it does get a little bit deep, and I've been really had to do some studying to kind of get up to speed on how to use this instrument. Once you kind of wrap your mind around it, it's really pretty simple. Yeah, the math can get a little bit complicated, but again, with a spreadsheet, it's just putting the numbers in there and it all calculates out for you. But this right here worked out extremely well. I'm very happy with the results I got. Again, we were well within spec for the length of the ways on this particular machine, well within spec, so I'm very happy with that. Next step, as far as the flatness goes, is we'll actually start scraping this to the table, and as we scrape it, it should get even better. But we are really and truly, even if we were to not do any scraping on this at all, at least from a flatness standpoint, we're good right now. So the other measurement that I wanted to look at, though, this kind of shows you how the two ways are in length. But I wanted to see how parallel these are in height to one another. So to do that, we use a little bit different test, not using the autocollimator, but using a precision level. And let me kind of get you set up and show you how I did that. So check the difference in parallel. These ways are parallel to one another in height. I use a test that's basically right out of the Conley machinery building book for doing two inverted V-ways such as this. And basically what I do is I've got two, these are actually precision ground rods. They're extremely, they're the same diameter, and they're extremely parallel and whatever to one another. I actually purchased these. They're almost like a gauge pin, but I had to get some pretty big ones, and they're the same size. And I lay a level across here. So I'm actually measuring the height of the ways. When I leveled the machine with the fell level, of course we were running on the top of the ways, which were ground at the same time, and in theory they ought to be exactly the same, but this is a more accurate way of doing it because we're actually measuring on the actual way surfaces in here. Got my stair at 199 master precision level on here. The accuracy of this level is 5/10,000ths, half of a thousandth of an inch per foot. These two are 14 inches apart. You do the math there, it comes out to about 5.8/10,000ths of an inch per foot. So every line on this bubble shows a change in height. If it moves one line, it's 0.00058 inches, or 5.8/10,000ths if you want to look at it that way. And what we do is we just see what our level is, whatever we're reading on here, and I'm not really worried. I know that this level is not perfectly calibrated, so I'm not worried about it not being level. My fell level is actually more accurate, and it has been better calibrated. But for what I'm doing, this is fine. It doesn't have to be calibrated to being level. I'm really not using it as a level. I'm using it as a comparator. I'm comparing the reading in one place to another. So we start here, we move the level down, we let it settle out, and we look and see where the level settles in here. And again, I can use some math and kind of figure out the differences in height as we move the level across the bed of the planer. And I did the same 10-inch increments. When I did this, we were just basically the worst error in here was about 1/1000th of an inch. So we are within 1/1000th of an inch of these two ways being parallel in height to one another throughout the length. Again, according to the specs in the book, when I looked them up, it's 2.5 thousandths of error that I have over this 10-foot bed. So again, we are well within spec as far as the elevation, the height between these two ways. Not worth trying to make any adjustments to make it any better. This is very similar to the way a Kingway system works. I've showed you that system before, but because we have the two inverted ways here, we really need something that rides down inside of both of them. And this method works out really, really well. If you're too far apart, you can put a precision ground parallel across here and put your level on top of that. In this case, my level was long enough just to bridge directly across them. I will point out, guys, that if you don't have an autocollimator, you can basically do a very similar thing by just using a precision level going across here. So I could have put my precision level on top of this sled and looked at the change in bubble as we go down, moving it from one position to another. And that would have basically told me the same thing that the autocollimator does. However, the accuracy of this level, even though this is a very precision level, 1/2 thousandth per foot, the increments that we're capable of reading off of it are much, much coarser than what we can get with the autocollimator. We can measure very, very precise angle differences with the autocollimator. This right here, you might be able to estimate half of a bubble, which would be, a 1/4 of a thousandth per foot. But the autocollimator is going to be extremely more accurate than this is. But if you needed to and didn't have the money or don't have access to an autocollimator, this is definitely an acceptable way to do the exact same thing we did. And quite honestly, it's probably going to get you close enough in most cases. Well, there you go, a little bit of discussion on how we went about getting this bed further leveled up and further aligned and getting it ready for actually scraping the ways to get it going. I cannot emphasize anytime you're working with a machine how important it is to get that machine set up properly. And yes, we're going to very extremes on this because I want to be extremely accurate. We've taken the time to have this bed ground in. But if I just went and plopped this planer down on the floor and didn't do any leveling or anything like that, we basically would have negated all the work and expense that we did to get these ways ground perfectly flat. Because again, I cannot emphasize how much, even though this is a big piece of cast iron, it's going to move. And when you set it down on the floor and you don't do any adjustments, it's going to move. Same is true with a lathe. You put a lathe on the ground, there's twists in that bed, there's differences in height. You need to take the time to level that machine out. And leveling is a little bit of a misnomer. It does not have to be perfectly level, but what is important is it's perfectly aligned. And you can use similar type methods as to what we're doing right here to get a lathe aligned. And I've talked about this before. On a worn lathe where you've got wear in the bed, you can actually correct some of that by purposely introducing some changes in the bed. You can actually bend the bed to make it where it comes into alignment better. And a lot of people don't realize that. And that's one of the little tricks that we've talked about in previous videos. So get your machine set up properly. According to the books, you're supposed to check the levelness of your machines about every 6 months once you get them put in, set up. And guys, here, I've been making some adjustments on this. I'm probably, before I come in here and scrape it, I'm going to recheck all this because just settling over time, it can make some small adjustments. And I want to make sure that we're starting out with everything exactly right. And this is the process that I went about doing it. The autocollimator, is it overkill? Yeah, you could maybe argue that it is, but I've got access to one, and we have been able to do a very good job of getting this machine set up. Autocollimator, they use this thing for calibrating surface plates, which are down to millionths of an inch in height differences, so extremely accurate again, and great for doing this. This is something else you can use one for. Wanted to share that, and I'm real happy where we are on this machine now. Really, the next big step is going to be scraping, getting this in here. I've got a few little things I got to get done before we do that. I've got to get some real heavy duty sawhorses in here where I can set my table on when I'm to do scraping or whatever. I've got to look, I want to do something about a lubrication system in here on this machine. This machine did not have any kind of lubrication system other than some way wipers that wiped oil on as it went back and forth. I wanted to upgrade that a little bit, and I need to do a little more research and a little more figuring out before we do that, but we're getting really, really close to actually to start scraping this bed in, and we'll bring you along for the ride when we do. Guys, that's going to be a wrap. I know we did a lot of talking in this episode, but hopefully you learned a little bit about alignment, learned a little bit about how to use an autocollimator, and see where we're at on the planer restoration project. Thanks for watching as always. Please subscribe to the channel if you haven't already. Comments are appreciated, and we'll catch you on the next video.